we are now ready to start talking about where magnetic fields come from. What are the sources of magnetic field? We've seen that if you have a magnetic field from somewhere, we haven't talked about where they come from yet, but if you have a magnetic field from somewhere, and then if you have a moving charge, it feels a force, and that force is proportional to V cross B. So that's what magnetic fields do to charges, in this case to moving charges. So what makes a magnetic field? Well, what we learned from experiment is that magnetic fields themselves are in fact made by moving charges. So if I have some charge, here's a charge, and it is moving this way, what we in fact learn is that as this charge is moving this way, it makes a magnetic field around it, and that magnetic field goes in a direction which curls around the vector that shows you the motion of the charge. So the magnetic field up here is coming out at you. The magnetic field down here is coming towards me. The magnetic field curls around the charge. It's very different in direction than in the electric field case. Also, the strength of the magnetic field is not the same in all directions. The magnetic field, if the charge is moving like this, the magnetic field this distance away from it is stronger over here than if I go over there. So here's the charge. I go the same distance that way or this way, and I get magnetic fields of a different strength. So we need a force law which tells us what is the magnetic field that is produced by a moving charge, which is to say that we need the magnetic analog of Coulomb's law. So let me just remind you of Coulomb's law. In Coulomb's law, what you said was here we have a charge Q, and we asked the question, what is the electric field over at this point here? Here was a point P, and we said, what is the magnetic field, the electric field right there? And the answer was that the electric field here pointed in this direction, and it had a magnitude which was given by K, Q, the strength of the charge, and then R hat over R squared, where R hat was a unit vector pointing in this direction, and R was this distance. So this is Coulomb's law. Everything we built, the first really 1/3 of 802 was built starting from Coulomb's law, plus the principle of superposition. Now we need to do the same thing for magnetic fields. We need to ask, suppose I have a moving charge here. What magnetic field does it make here? So let me erase the electric field and the equation for the electric field. I'm going to keep R hat and R because they're going to play a role again. But now let me make this charge move. And let's say that this charge is moving in this direction. So this charge is moving with the velocity v. And let me now ask what the magnetic field is at this point P. So what is the magnetic field at the point P? Well, I'm going to start by telling you the answer, and then we're going to walk through all the parts of the answer. Here's the answer. I want to know what is the magnetic field at the point P. Well, it has a Q in it, and it has a 1 over R squared in it. That's the same as in Coulomb's law. The magnetic field at this point P is falls off with distance like 1 over R squared. But wait a minute, I just said that the direction mattered. So there must be something funky to do with the vectors. And there is, because what is the direction of the magnetic field at this point P? It is not in the R hat direction. R hat, the electric field was in the R hat direction. So there has to be another vector in the problem, and there's the velocity vector. The velocity of the charge is here. So, well, okay, so maybe the magnetic field is in the V direction, pointing this way. Well, that's not the case either. That's not what we learn when we do experiments to measure the magnetic field created by a moving charge. It's not pointing in the V direction. In fact, it's pointing in the V cross R hat direction, which means that the magnetic field is perpendicular both to the velocity and to R hat. So if I ask what direction does it point in, you should get out your right hand and do V cross R. V cross R, that gives me a vector that's pointing away from you towards me. So we represent the direction of the magnetic field in this way. It's a vector pointing from you, away from you, towards me. That's the direction of the magnetic field at this point P, created by a moving charge. The charge is located here and moving this way. So let's look at all the pieces here. The strength of the magnetic field, the magnitude of B, is given by Q times the magnitude of the velocity divided by r squared. And I left a blank space here. We need a constant of nature here, the analog of K. And that constant of nature is written mu naught over 4 pi. So mu naught over 4 pi is a new constant of nature. In fact, I'll tell you the value of mu naught. So this mu naught over 4 pi is the analog of K in Coulomb's law. It's 4 pi times 10 to the minus 7 Tesla meter per ampere. At this point, you should be scratching your head a little bit. How could it be that a fundamental constant of nature that can only be determined from experiment has the value of precisely 4 pi times 10 to the minus 7? That should be bothering you. But so where does it come from? It comes from our choice of units. The choice of the Coulomb, which was an arbitrary choice made at the beginning of 802, the reason for that arbitrary choice, and as opposed to picking something else for the Coulomb, was I made that choice so that the mu naught, the value of mu naught in our units would turn out to be really nice. So this is actually a fundamental constant of nature. It has to be measured, but we've defined our units so that this constant of nature takes on this particularly simple value. Okay, so let's look at this expression. The magnitude of the magnetic field here is given by Q times V. That means that if the charge is not moving, there's no magnetic field. And the magnetic field here that you get is proportional to the magnitude of the velocity of the charge. Divide by r squared. And then there's this V cross r direction. So we already saw that V cross r is a vector that points away from you towards me. So the V cross r is telling you the direction. But V cross r is also telling you something interesting about the magnitude of the magnetic field. Because you see, V cross r, that's a vector which is perpendicular to both V and r. But if V and r get to be parallel, then V cross r goes to 0. And if V and r get to be perpendicular, then V cross r takes on its maximal value, V cross r hat. So what that means is that if I look at the magnetic field here, and then I look at the magnetic field here, and then I look at the magnetic field there, this is 3 different locations. So this is, let's say, P1, and this is P2, and this is P3. There's 3 different points, P, P1, P2, P3. I picked them so that they were all the same distance r away from the charge. So r is the same here, V is the same, Q is the same, r squared is the same. What's different is V cross r hat. And V cross, for these 3 points, V cross r hat is biggest here, somewhere in the middle here, and it's almost 0 there because if I go to this spot, r hat is almost parallel with V. So this force law, which I'm going to put in a box, describes the fact that I started with, that if I have a moving charge moving like this, the magnetic field that it creates is in a direction which curls around the momentum vector, curls around the velocity vector. So over here, it's coming away from you towards me. Over there, it's going in the opposite direction. Right here, the magnetic field is coming towards you, away from me. Same with here. Same with here. So the magnetic field curls around the velocity vector, as I've been showing. And it is strongest, of course, it's strongest close to Q. That's the 1 over r squared. But it is also strongest in this direction relative to this direction or relative to this direction. So the place where the magnetic field is strongest when the moving charge is right there is going to be here and here. So this then is the analog of Coulomb's law for magnetic fields. This tells us what is the magnetic field that's created by a single moving charge with velocity v. And we will be building consequences from this for the second third of 802.